Okay, so we're back on the reaction business. So what I would like to discuss this afternoon is the few body model of breakup reaction. So we've seen so far only the way to describe the elastic scattering, and during the exercise this morning, we've sort of seen a way to include the breakup channel by including this diffuse, so long range surface term in the optical potential. But this is very phenomenological. So we would like to be a bit more precise and somehow to answer Enrico's question this morning. We'll see how to try to have a better description of the reaction, of that particular reaction we've looked today this morning. So beryllium 11 on zinc 64. So what I will do is first explain what I call breakup reactions. We had an idea of that this morning, and then discuss the few body model of reactions. And then what we'll do is to look at three different ways to solve the Schrödinger equation. So there is the one which is fully quantile, and which is a coupled channel method. It's called CDCC. So CD stands for continuum discretized, and the other two C's are for the coupled channel. And then we'll see the time-dependent approach, which is a semi-classical approximation. And yeah, we'll just see once the first order of the perturbation theory. I have no idea why it appears twice, but anyway. And then we'll see the Eichoner approximation, which is a higher order, a higher energy approximation of the reaction. And I would like to illustrate, I will illustrate the three different methods in a comparison for the Coulomb breakup of carbon 15. So another 1 neutron halonucleus. So we'll see how they compare to each other. What are their strengths and what are their weaknesses in each of the cases. So as I said this morning, what I will discuss is the actual dissociation of a projectile into its more into its constituents, so clusters of nucleons, through the interaction with the target. So we've seen this morning an example. So beryllium 11 breaking up into beryllium 10 and a neutron. If you take boron 8, which is supposed to be a 1 proton halonucleus, well, it's a very loosely bound system. It's bound by 130 or 40 keV into beryllium 7 plus P on a lead target. And of course, the whole problem, you could say, okay, let's solve it ab initio. We consider all the nucleons, but that starts to be very complicated to solve. First, not only just solving beryllium 11 or boron 8 as an 11 or 8 body system is complicated, but the target also is complicated, and then you collide, you smash the two guys together, and that makes the whole thing very complicated. So what we usually do is we rely on the the different energy scales and the cluster structure of these nuclei. And so what will happen, this is a figure that I stole from Antonio Moro. So you have beryllium 11 seen as a beryllium 10 core plus 1 valence neutron impinging on a target. And what happens is the target will act differently on the core and on the valence neutron. So if you just think of the Coulomb interaction, of course, the neutron is insensitive to the Coulomb interaction. So at large distances, it won't feel any effect from the target, but the core will basically be repelled. And because the system is loosely bound, this can lead to the breakup of the system. This leads as a tidal force on the system. So the two components of the nucleus do not interact in the same way with the target, and so that induces an internal force that breaks up the system. And so, of course, if the system is tightly bound, that has little effect, but for a loosely bound system as beryllium 11, as we've seen this morning, just on the elastic scattering, that has a significant influence. And so you can learn something, hopefully, from measuring this, seeing how they break up, in which at which energy, what's the energy, and and what's the value of the cross section, will give us hopefully information about the structure of the nucleus. And so I will look mostly as a way to study the cluster structure, and also tomorrow we'll go more into the details about what can actually be inferred from such measurements. But it's also used to infer rates of reaction of astrophysical interest. So especially for the boron 8 case that has been used a lot to try to infer a radiative capture cross section. But in order to do that, you really need to understand what's going on. You need to understand how the reaction proceeds, what's the reaction mechanism, and so you need a good description of the reaction, which includes a realistic model of the projectile. So you need both, but you can't go to too complex a description of the projectile, because otherwise it's too expensive. So just to emphasize what I said this morning, I'm looking here at the elastic breakup, so all the clusters are measured in coincidence. This is what we call an exclusive measurements. So you measure the core, you measure the neutron in coincidence, sometimes even the gamma in coincidence. You don't do any other approx. You do not. That's what you do. So it's not a knockout reaction where these guys here would not be measured. That would be a knockout reaction. So the framework we use is a few body description of the reaction. So that's really the important part. It's a few body. It's a few body model of the reaction. We assume that the projectile is described. So I will focus here on a two body, so a one neutron or one proton halo nucleus. And I assume that the projectile is seen as a bound state of a core, of which I will not consider the internal structure, a fragment, which is this valence nucleon, and a target, and I will also neglect the structure of the target. So it's a very simple model, but it makes sense when you think at the energy levels that you consider, and the channel of the reaction that you're looking for. So this system is described quantum mechanically with an effective two-body Hamiltonian. Well, so one-body Hamiltonian, because you remove the center of mass motion, and the interaction between the core and the fragment is a phenomenological potential. We'll see in more detail tomorrow, hopefully, what we can take for that interaction, but it's a potential that is adjusted to reproduce what you know about the system. So the binding energy, spin and parity of the first states. The target is assumed to be a structureless particle, and the interaction between the core and the target, and the fragment and the target, will be described by optical potential. So that's why it was so important to know this notion of optical potential. So we will assume that all the other channels, so channel in which the neutron is absorbed by the target, or the core collides with the target and leads to a fragmentation reaction, breaks up into pieces, deeply inelastic reaction, everything is absorbed into this imaginary part of the optical potential. And the only thing that we have to solve then within this framework is to solve a three-body Schrödinger equation. Okay, so that simplifies a lot the system. So the projectile Hamiltonian has this form, so the kinetic term plus the core fragment interaction, and it's usually of a Wood-Saxon form. So the negative energy states are the bound state of the system, so what you know about the bound state of the system, and for the positive energy, it has a continuum spectrum, and that corresponds to the continuum of the system. So where the fragment dissociates from the core. The breakup is just a transition from you start from a bound state and you go to the continuum. through the interaction with the target. So that interaction leads to this tidal force, and it leads to the breakup of the system. Both Coulomb and nuclear interaction will play a role, and we'll see that can pose be a problem when you want to describe these reactions. Breakup can take place in one or more steps. We'll see that back tomorrow. There is a dynamics of the reaction. You have coupled channels, so you have a coupling effect in the continuum. It's not a very simple discrete reaction that takes place in one step, and it will be sensitive to both the bound and the continuum state. We'll see that in more detail tomorrow. So I will give some examples on the description of on beryllium-11. So here is here is the spectrum, the low energy spectrum of beryllium-11. So we'll assume that beryllium-11 is a beryllium-10 nucleus in its 0+ ground state plus just one valence neutron. And so beryllium-11 has two bound states. The first one is bound by only half an MeV. The spin is 1/2 plus. And so it can be described as an S1/2. So we've seen what Tom Aumann showed and what we've seen this morning. The knockout reaction that he measured at MSU showed that it was most likely an S wave. The ground state was an S wave compatible with the value of a 1/2 plus. So the ground state, the system is bound in the S wave. The first excited state is also bound, and it's a 1/2 minus state, and it is therefore described in the PIERRE. Note here that there is a shell inversion. So if you look at the extreme shell model of the system, so if you just look at the neutron in the beryllium-11, so you start with the 0s1/2, then the next one is the 0p3/2 shell, and then you have the normal ordering gives you the 0p1/2, and then you have eventually so there is shell closure here, the 1s1/2. And so in beryllium-11 you have seven neutrons. So beryllium has 4 protons, so it makes seven neutrons. So you have 2 in the 0s1/2, you have 4 here, and so naturally you would think that the next one comes here, but that would lead to a state that has a spin of a spin and parity 1/2 minus, and it's actually this state here. So you have a shell inversion. What happens in reality is that you have this shell here comes down. It's mostly due to the tensor force because of the system being very asymmetric, and what happens is that you actually have the 1s1/2 shell that comes down, and the neutron is in this shell, and that leads to this state here. Above the 1 neutron separation threshold, which is here, you have a 5/2 plus resonance, which you can also describe as a d5/2 neutron, as a d5/2 neutron in not bound, but interacting with beryllium-10 with the beryllium-10 core. Yeah. Mm-hmm. Yeah, when you look at the microscopic model, so not this simple model with the beryllium-10 10 core. So this is something I've heard from, well, Nakamura, Tanihata made a presentation recently about that, but it's a Japanese group who worked on that, and they tried to understand, because also you could see also a shell inversion in lithium-11, so where you have also the S wave coming down, and they tried to understand, and it seems that there is an effect due to the asymmetry between the number of, it's always in a system where you have lots of neutrons and a rather small amount of protons, and that this at one point plays a role to change the ordering of the shells when you approach the drip line. I don't know if you. Yeah, yeah. Mm-hmm. 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 Yeah, yeah. As frozen. Yeah, yeah. Mm-hmm. It's very simple. Mm-hmm. Yeah, 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 yeah. Yeah. No, 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 no. It's not. It's not. It's not that simple. So there is a microscopic calculation, ab initio calculation, by the group of Navratil and Robert Roth, and they manage to reproduce this shell inversion, but it's really hard work. So it's very complicated to understand that. But there is no very simple model that can lead to such shell inversion. So you need to put it by hand in the model. So what you do is the potential in the PIERRE half and in the ESSER half are not exactly the same, and you adjust the depth in order to reproduce the correct binding energy. Now, that was an example for the core neutron interaction. What about the interaction between the core and the target and the neutron and the target? Well, we use what I've mentioned, optical potential, and so you choose them in the literature. The most problematic is this core target, because as I said, if you take these Wood-Saxon potential, they are fitted at one given energy for one given system, and as theorists, we have complained with the experimentalists that we don't have these optical potentials. So we would need help. We would need elastic scattering data to fit potentials. But if an experimentalist goes to a PAC, so Program Advisory Committee, to ask for beam time to measure elastic scattering to get an optical potential, nowadays you will never get the beam time. So it's out of question. So that's why there is this strong endeavor to try to get these optical potential from first principles. And as I've said before, for a nuclear target interaction, then you have global optical potentials that are more reliable. So you can use Beckety-Greenlees, Chapel Hill, Koning de la Roche. These are the options that you have. So you have all the ingredients. Now the only thing that you need to do is to solve that problem with the initial condition that the projectile is in its ground state and it's impinging on the target. So okay, so it comes here with a plane wave, which is distorted, of course, because you have Coulomb at a large distance. So you need to take that into account. And there are many different ways to solve this problem. So we have published a chapter on this. I usually say it's recent, but you will probably think that it's a bit old. And so what I will do is focus mostly on CDCC, so the couple channel with a discretized continuum. So this is purely quantal, semi-classical approximation using a time-dependent approach, or the icon approximation. There are other ways, but I won't discuss them. In all the discussion here, I will neglect spin. I will not consider spin, just to keep the equations to a normal level of complexity. I don't want to go too much into the detail. So let's see the CDCC technique. So the goal of the idea that is behind CDCC is that the basis of the Hamiltonian, so the eigenstate of the Hamiltonian H naught, which is the Hamiltonian that describes the projectile, form a basis in the R space. So in the projectile, in the core neutron relative coordinates. So the idea is basically you expand the three-body wave function onto that basis, and then that simplifies that leads to these couple equations. So what you need to do is you have your kinetic term for the projectile target relative motion. You have the Hamiltonian H naught of the projectile plus the interaction between the core and the target plus the interaction between the fragment and the target. Okay, and this three-body Hamiltonian acts on that three-body wave function. But what I will do is use this. I will use this expansion. So what I will do is so you will have chi, which is here for the relative motion between the projectile and the target, and so it's a coefficient expansion of that in that basis phi. And so my equation is the total energy. This Hamiltonian applied on the wave function equals the total energy times the wave function. And what I will do is project this on one of the other states, so phi j in this case. So what I will have is I will look at each of the different terms. What I will have is sum over I. Of course, the kinetic term here acts only on that function, not on that function. It does not act on little r. So what I will have is phi j over phi I tr on psi I plus I phi j h naught I plus phi j vct plus vft. I group them together, okay, because they are diagonal neither in the R space or in the capital R space, so projectile target relative coordinate, or nor little r, so the core fragment relative coordinate. And this is equal to ET. Yeah. Sum over I phi j phi I. And now we can look at each of the different terms. This, of course, there are two, the basis is orthogonal. They correspond to different energies. So this is equal to delta I to delta ij. This phi I is, both are an eigenstate of H naught. So what we know is that it's equal to a Ej delta ij. Here you have, this term here is completely non-diagonal, so it's something that really couples the different channel. We'll see that in a moment. And here again, we have delta ij. So what I can do is rewrite this as tr psi j plus sum over I phi j VCT plus VFT phi I chi I, and this is equal to ET minus EJ chi j. Okay. So what you have here is what you have here is just a Schrödinger equation, but you have a coupling here. You have different channels, so it's a set of equations that are coupled to each other, and they are coupled through the interaction. So if you think it as what I've said, so you go from the bound state and then it can be broken up, you go to another channel, it's because of these two interactions, which are not exactly the same. So you induce this tidal force, and that's exactly what I said. So this is a quantum mechanical way to see what, demonstrate what I've said, that the tidal force induces these coupling between the different channel. So this is a clear way to write the equation with this coupling term. And so here is a drawing of what's going on. So in this case for carbon 15, sorry, I will change from carbon 15, beryllium 11, depending on what I have. I like the drawing, and it's a picture from Jeff Tostevin. So you have here the spectrum. You have the 1/2 plus bound state. You have a 5/2 plus, in this case, excited state, and then you have the continuum. And what happened is that you can go from different partial. You start from the S wave, and you can go to the P wave, but then you have coupling in the continuum. You couple here within the continuum. You couple to higher partial wave. This is what you need to do when you solve this equation. Now this is all good. I've used the different eigenstates and I've done a sum over I, but we have a big problem. These are not discrete states, it's a continuum. So I should replace the sum that I wrote before by an integral. So you have an infinite number of states. So it's an infinite dimension of the problem. So we're stuck. So either you stop there, start crying, and then you change business, or you do something, and that's what George Havicek did in the 70s. And he said, well, we do as we usually do for the continuum. We discretize everything. When you solve an equation on a real variable, what you do is you discretize that variable, and then you move on, and it works. So his idea was, you say that continuum wave, I change it into a discrete state, and that's actually what is illustrated here by Jeff's drawing. So you basically build sort of bins of the continuum to try to discretize that continuum. So there are different ways of doing. The first one is what George Ravitcher suggested initially. You divide the continuum into bins, okay, small bins, okay, not too big, but small bins, and then you choose the middle one. You choose the middle point, and you say that's fine. Now this is good. This is a good first approximation. The problem is that these wave functions, as we've seen before, are not L squares. They are not square integrable. And this is a problem when you want to compute the matrix element of the coupling potential if it's a long range. So if Coulomb is involved, and Coulomb is always involved, you will run into problems because the wave function never stops. It's always oscillating, and Coulomb decays very, very slowly towards infinity. So that's a problem. So there came another idea, mostly by a Japanese group, and it's to sort of, instead of taking the center, the center of the bin, you take an average of all the wave function in the bin. And because of that, you have all these sine and cosine function that we've seen before, but with slightly different values of the momentum of the wave vector, and that makes that they all cancel to each other, and you can build square integrable wave function through that technique, and this is what we call the binning technique. Okay, so what you do is you build an average, so you build these continuum wave function, and then you make an average of them within the bin, and that leads to a wave function that decays at large distances and makes the calculation a bit easier. Another way of doing of getting square integrable functions is to use pseudostates. So you, in a nutshell, you solve the Schrödinger equation, that Schrödinger equation, in a box. So you put your nucleus in a box, and of course, at the boundary of the box, the wave function has to vanish. So you basically have a discrete state of a discrete set of state, and this is what Thomas Drouin did during his PhD thesis in Brussels. So building these pseudostates and then use them into a CDCC calculation. And then a fourth way is something that was developed at Sevilla. So it's the THO, transformed harmonic oscillator basis. The idea is you map. So when you take a harmonic oscillator, it's basically a box. So you have discrete states. So you have all these states, and the idea is you get a mapping from these wave functions to the wave functions that you want to describe to these wave functions. And so you take away how to, for the bound state, you map the bound state from your actual Hamiltonian to the ground state of the harmonic oscillator, and then you use that transformation invert to obtain a discrete continuum. Here is the reference of the original idea, and that's the method that is used intensely by the group of Sevilla to discretize the continuum. So you have different ways to solve to get this discrete discretization of the continuum. And then what do you do? Well, you do as what we've seen on Tuesday. So you expand the projectile target relative motion, the projectile target wave function into spherical harmonics. So you do a partial wave expansion. So you should start to be familiar to that expansion. That leads to a radial equation with coupling term. Okay, that's just a partial wave expansion of these coupling terms of the interaction. And asymptotically, exactly as what we've seen, for exactly the same reason, because this interaction includes Coulomb, but the nuclear term, so it's short range, and so asymptotically they should behave as an incoming Coulomb wave plus a phase shifted outgoing Coulomb wave. So you have an incoming Coulomb wave, outgoing Coulomb wave with a phase shift. Now, this is the interesting point. What we've seen before, in all the cases, we've seen this S matrix, but the S matrix was just a number. It was just E to the power 2 times I delta L, where delta L is the phase shift. Here you really have a matrix, because you have these different channels, so you can couple different channels. So you really get an S matrix. So you really get a matrix in your calculation. And from that S matrix, with a little bit of math, you can build a sort of scattering amplitude, but that includes a breakup amplitude. That includes so an amplitude in all the different channels that you can have, which has this kind of expression where the S matrix appears once again. And the breakup cross section is obtained as always as the sum, in this case over the different contribution of the square modulus of this sort of scattering amplitude. Okay. So it's very similar to what we've seen before, but it's much more complicated. I would like to emphasize one point, is that this method properly accounts for energy conservation. So the energy is always conserved here. The value of this K here is the incoming wave number. K prime is the wave number in the scattering channel, and K prime is related to the initial energy of the system, the initial kinetic energy, but also the energy in which the projectile is, so in the continuum or in an excited state. So you have a proper conservation of energy taken into account in this model. So that's one of the very important point of CDCC. It's fully quantile. There is no approximation performed here, but for the discretized continuum, and it conserves energy. So it's very convenient. So there are different methods, different reviews written on CDCC. So I like this. This is one of the original papers. It's mostly by the Kyushu group. There is this paper by Tostevin, Nunes, and Thompson, which is very good to know how to get the cross sections from the result of the calculation. And there is a recent, I should pay attention to that. I should update these slides, because I guess that for you 2012 was probably not that recent. But by Yahio-san and collaborators, so also the Kyushu group. So as I said, it's fully quantile, it conserves energy. There is no approximation for the projectile target motion, so everything is fine. The problem, it's expensive. So it takes a few days to get one reaction calculation when you run in parallel on 4 or 5 nodes. So it takes time. It's a time-consuming calculation. There are various codes. So Kyushu group is very well known. So it's the Kamimura-san group, Kamimura and Yahio. But the best known code was written by Ian Thompson. It's Fresco. You can download it freely from that website. Do you want to make the break now? Then it's fine. Then I can go on. Yeah. Okay, very good. So here is an example. So that's a calculation by Jeff Tostevin. Oh, sorry. Yeah. I don't think so. So, but it is an approximation, so you need to keep that in mind. And sometimes you need to remind the people doing CDCC that they do some approximation. So this is an approximation. And so one of the things is that you need to make sure that you have properly converged, that you go high enough in energy, because that's one of the limitation. The higher you go in energy, in energy, I mean, sorry. I mean, that maximal energy, how far you need to go, you need to check that. How many bins you include there, how many states you include. The higher number of states you have, the more precise you are, but also the longer the calculation. So so this is something that you can somehow test. If you have a finer grid in the continuum, then you can, and your calculation is stable. That means that the discretization works fine, hopefully. Yeah. Mm-hmm. 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 Yeah. So here, so the paper have arrived, but I will finish the illustration. So this is an example for the boronate. It's the breakup of boronate on nickel 58 at low energy. It's an experiment performed at Notre Dame, University of Notre Dame. in Indiana, and that was done by Guimaraes and collaborators. And this is the analysis by Jeff Tostevin. So the points are from this paper, and the analysis with the CDCC was performed by Jeff Filomena Nunes and Ian Thompson. And what you see is that they can very nicely reproduce the data. Once they have converged, the difference between the dashed line and the solid line is an issue of convergence. So you need to check that convergence. And then something that you will probably be a little bit more sensitive to is this set of data. So I'm back to this paper by Alessia Di Pietro. So so I told you this morning that they performed the calculation. They performed the measurement, sorry, for barium-10 and barium-11. That's true, but they performed barium-9, barium-10, and barium-11. And so it's a nice paper. It's an excellent experiment, but it's a crappy figure. Anyway, that's what happens when you use Excel to get your figures. Anyway, so the barium-9 points are in red, then the barium-10 points are the blue ones, so that you know these points, and the black squares are the barium-11. And so what you see is that barium-10 and barium-9 behave exactly in the same way, and you can fit them with optical potential. But then when you move to barium-11, what happens is you have this loss of flux. And so that was explained phenomenologically by, I think it was Angela Bonacorso who came up with the idea. So to have this diffuse optical surface term that managed to reproduce properly the data. But the question, of course, is then what? Is there a better way to do it? And of course, there is a better way. You do a CDCC calculation. It's a low energy reaction. It's only CDCC will really be working. And so they worked in collaboration with Antonio Moro from Sevilla. And so they performed the calculation. They performed the CDCC calculation. So let's start with something which is not CDCC because there is no continuum. So it's not a CDCC, there is no continuum. Anyway, so they did a calculation, just usual. It's basically equivalent to a DWBA calculation, no coupling to the continuum. And what happens is you get this curve. So you get exactly what we've seen before. And what you have obtained when you just switched the change slightly the masses, so nothing happens. But once you include the continuum, you have the full calculation. That's the blue solid line, which is here. You are exactly on top of the data. So it works very well. So including, this is really the demonstration that when you include the breakup channel in your calculation, you can reproduce the data. And now to go back to Enrico's questions, yeah, you can't really explain these oscillation there with that method. When you're a theorist, you blame the experimentalist. You say, okay, you don't know what you're doing. You blame the systematics because it's just the statistics here, the statistics uncertainty that is here. I don't think that you can really have an angular resolution that fine to really disentangle these modes of oscillation. It's probably just due to statistical oscillations in the calculation. Okay, so, but as I said, this is a very computationally challenging calculation. So there are other approaches that enable to reduce the computational time. And so I can stop now, and you can hand out the papers, I guess. And we can make a short break so you can stretch your legs. And so I suggest we start again. And so, as I said, we've just seen the CDCC method, saying that it has lots of advantages. It's fully quantal, it conserves energy, And so it has no approximation between the projectile target relative motion, but it's really expensive on the numerical viewpoint. So it's a very difficult. It's a method that is difficult to run. You need bit computers, and so so people have looked at different alternatives, and one of these alternatives is it's the time-dependent approach. So the idea is to simplify the projectile target motion. So instead of treating it quantum mechanically, you go for a semi-classical approximation. You say the projectile target relative motion is described by a classical trajectory. So here, it's looked in the reference frame of the projectile. So you sit on the projectile, and so you see the target moving, passing by. That's exactly the viewpoint. The viewpoint here. So you still describe this exactly quantum mechanically in exactly the same way. So you can take the same Hamiltonian. You can take the same interaction between the target and the fragment, and the target and the core, but you simplify the calculation of the relative motion because you assume it's a trajectory. And so what you need to solve is to solve. So what you assume is that the projectile feels the field created by the target as an external time-dependent field, because the target follows this trajectory in the projectile rest frame. And so what you need to do is to solve a time-dependent Schrödinger equation. And so you start from you start from the bound state, and then you evolve and you solve that the time-dependent Schrödinger equation. So how do you do that? You can solve that approximately. You can do a first-order perturbation theory, but you can go a little bit more precise, be more precise, and solve it exactly. And so what you do usually is you do an approximation of the evolution operator. So you assume that the wave function computed at time t plus delta t is obtained from the wave function at time t, to which you apply this time-dependent evolution operator. And the evolution operator is just the exponential of the integral of the Hamiltonian. However, building the exponential of an operator is not an easy task. So what we usually perform is do two approximations. The first one is to say that is to split this Hamiltonian, because the Hamiltonian has two parts. You have one part which is H naught, which is the Hamiltonian describes the projectile, and then you have another part which is related to the interaction between the projectile and the target. And so what you do is you make an approximation, and you say it's the product of two exponential minus I over H bar H naught delta t e at the power minus I delta t over H bar v of t, and this is of order 2, so it's not an excellent approximation, but it's good enough if delta t is small enough. So there are two approximations. First, of course, you have the integration, which is simplified, but also you split the operator. You start from one exponential and you end up with two exponentials. This is true for numbers. This is not true for matrices. You have, if the two matrices do not commute, which is the case here, if the two operators do not commute, you cannot just split these two operators. You need there are other terms in this expansion. So this is not fully true. But that's an approximation, and the reason is that you can express easily these two operators in different bases, and so what you do is you apply one part in one basis, you change base here, and then you apply this one in your algorithm. You apply the two different parts of the operator separately in different bases. This makes the thing a little bit simpler. And so one way to do that, to compute, or just computing these operators is not simple. So what we usually do is use a PIERRE approximation. Where E at the power I delta T over H bar times A is approximated by 1 minus delta T over H bar A, 1 plus I delta T over 2H bar A minus 1, and this is of order 3. So this makes computing, you don't need to compute the exponential. What you can do here is just, this is very simple to do. This is more complicated because you need to compute the inverse of an operator. So it's slightly more complicated, but it's easy. The reason why we do that and not the usual approximation is that this is unitary. And so you conserve the norm of the wave function. If you use the usual approximation, if you said this is just 1 minus I delta T over H bar A, then the problem is this is not unitary. And so the problem is that you will not conserve the norm of the wave function, and you don't know exactly in which channel that norm will go. Will it go into the elastic scattering? Will it go into the breakup? So this is a problem. This is not a good approximation. So that's why we don't consider this kind of approximation, which would be much more simple. And so yeah. 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 No, the reason why we do the splitting here usually is because this one is more diagonal in one base and this one is more diagonal in another base. And so you want to be as diagonal as you want, as possible, because otherwise you need, inverting a diagonal operator is piece of cake. The fuller your matrix, the harder the problem is. And so that's the reason why we split this into two parts. And so we'll see there are examples then, there are different ways to solve to different bases that you can use and different ways to do it. And so it's that's why we do these two steps. Of course, if you are working just in one basis, then there is no reason to do this split, and you can just do that with the whole operator. The problem is that this one and this one are usually not diagonal in the same basis, or more diagonal, or less. So the matrices are less full in one basis than the other. So it's way faster. But the problem is that it's a semi-classical approximation. So you do not include quantal interferences between different trajectories. So it makes the whole thing more, it's less reliable, okay? It's a less good description. So this is what I wanted to say. So there are 3 codes that are based on a partial wave expansion of the wave function. So you do exactly what we've seen before. So the first 3D codes was performed by Kido, Yabana, and Suzuki in 1994. The next one came with the code by Henning S. Benson, George Birch, and Carlos Bertolani in 1995. And then Stefan Tüpel and Hermann Wolter have published a code in 1999 doing that. So Hermann Wolter was in Munich. Then the best code, of course, is working on a 3D spherical mesh. That's where you really have this idea of the Hamiltonian is diagonal in one base and the potential is diagonal in another. So that's something we did in 2003. And then there is an expansion on the 3D cubic lattice. That's a very, it's a very interesting work by Monique Fallot in 2002. So they work on a cubic mesh, and also there they have two different bases to describe. So there they do a separation slightly different. What they separate is not H0 and V, it's the kinetic operator of H0 and all the potential. And what they do, because they are on a cubic lattice, they use fast Fourier transform to treat the kinetic operator. And so there they have a kinetic operator which is diagonal in one base, but they have to go back to the mesh to describe the potential. So it's a similar idea. Okay, so what you do is you do the evolution until large enough time that your wave function does not change anymore. You project it onto the different states. You take the square models and you get a breakup probability for each of the trajectories. And then what you do is there is an angular relation between the scattering angle and the impact parameter. And when you integrate over the angles, you integrate over the impact parameter, and you get your total cross section. So this would be the breakup cross section as a function of the energy between the core and the halo nucleus, the halo nucleon. Initially, these equations were solved using a perturbative method, first order of the perturbation theory. This is something you probably have had in your quantum mechanics classes. The method was mostly developed by Alder and Winther in the 70s, so to have a perturbative expansion. And here is the expression of these matrix elements. So this is the solution, but you have it's a one-step transition from the ground state to the continuum through these interactions. And we'll see in a moment that this is sometimes not enough, okay? And so you have here the expression for the Coulomb, purely Coulomb interaction. You can have analytical solutions. So that also makes the thing very, very easy. Your code runs in a few seconds and you get an estimate for the cross section. So which is ideal, but you have no nuclear interaction, and you do not include higher order effects in the calculation. And here is an example by Henning S. Benson. He performed his calculation with his code for the Coulomb breakup of carbon-15 on lead at 70 MeV per nucleon. The data are from RIKEN as usual. So you see here this breakup cross-section as a function of the relative energy between the carbon-14 and the neutron after dissociation. So carbon-15 comes, it breaks up into two, and you have the core, you have the relative energy between the core and the neutron, and you obtain these data. There are two selections in angle, so just the forward angles or all the angles in this case, and so that's the reason for the difference. The dynamical calculation is the black line, and the first this is the full dynamical calculation, and then it's scaled to the data. It's the red line. So you have a very good agreement with the data after folding with the energy resolution, etc. When you do a first order perturbation theory calculation, as I've mentioned before, you see a strong difference between the data and the experiment. So if you infer information from these calculations, you will be wrong. So that the observables, the structure observable that you will obtain will be wrong, and the change is significant. You have up to 20% difference there in the calculation between the E1 first order, between the first order calculation and the dynamical one. You have nearly 20% difference. So this is really significant, and so you need to take that into account when you analyze these data. And tomorrow we'll discuss more into the details, these dynamical effects. And so the third approximation that I would like to discuss is the Eichner approximation. This is a high energy approximation. This is the equation that we want to solve. And we want to solve that with the initial condition that the projectile is in its bound state and it's impinging on the target. And at high enough energy, this is something that only the experimentalist understand. So it's the wrong audience. But I'm trying to explain you. So if you are at high energy, all the fragments will be scattered at very forward angle. So everything is so when you measure this kind of reaction at high energy, the detectors are there at very forward angle. You never put any detectors at 90 degrees or even at 45 degrees. Everything is scattered at very forward angle. And so what this means, it means that most of the dependence on the relative motion between the projectile and the target is in this plane wave. Because even what's scattered away after the dissociation is still moving basically on a straight line or a very nearly as a plane wave here. And so the idea of the Eichner approximation is, let's take that into account and simplify the problem, and let's factorize that plane wave out of the wave function. So what the idea is, you take this wave function and you factorize the plane wave out of that wave function, and you define a new wave function that I call here psi hat. Okay, here there is no approximation. So here there is no approximation so far. It's just that we do this, and so we'll put that expansion or that factorization. We'll put it in the equation, and as you can see, this term here is only affected significantly by the kinetic term. So let's look at what happens because of the kinetic term on that wave function. So the Laplacian on the wave function will actually be the second order derivative over x squared plus the second order derivative over y squared on e to the power I k z and then you have psi hat plus the second order derivative over, I should have put the, because it's capital Z, I'm sorry. So this should be x and z square e to the power I k z. That's the plane wave, and that's my psi hat m0 over here. So I won't discuss this because nothing happens. You can factorize that. You can move it here. It does not affect this part. So I will just look at what's happening here on that term. So the second order derivative of z squared of e to the power I k z psi hat m0, what it gives, it's the first order derivative of I k e to the power I k z psi hat m0 plus e a k z, and then the first order derivative of psi hat. And so this will be equal to, I reapply that, so I will have minus k squared then this will work on this, but then it will also work on this one. So I will obtain twice the same term. So I will have twice I k e at the power I k z derivative over z of psi hat plus IKZ second order derivative of psi hat. I don't need to close it here. So far, no approximation. It's just a regular calculation. Now, the whole idea is that most of the dependence on Z will be contained in that plane wave. So what you will assume is that psi hat will be smoothly varying with the Z, with capital R. Most of the dependence will be in the plane wave. And so the idea of the approximation is to say that this second order derivative is small. So the idea is to say that is much smaller than K first order derivative of psi hat. Okay. And there are two reasons. First, you have only a single differential, single derivation here, and you have a factor of K. If you are at high enough value, K will be rather large at high energy. And so the idea is that in the end, you will be able to replace to approximate this by minus K square, sorry, E at the power I K Z psi hat plus twice I K E at the power I K Z derivation over Z of psi hat. And you neglect everything else. So you neglect all the second order derivations because you assume that the projectile will basically be located mostly at a very forward angle. And so what happens next is that when you compute, when you write the equation, what will happen is you get h bar square over twice, over twice mu K square E at the power I K Z psi hat M0 plus minus, sorry, h bar over 2 mu 2 ik plus h naught. And the other three terms do not have much of an influence. And this is equal to the total energy E at the power a kz psi hat. And here we can simplify, so you see that all the exponential can be cancelled, and then you can account. You can do two approximation, or not two approximation. You can count on two things. The first is by conservation of energy, the total energy is equal to h bar square k square over 2 mu, which is the kinetic energy of the relative motion between the projectile and the target, plus the initial energy of the projectile. And so taking that in, you can therefore subtract that term from this term to obtain something which is a bit more simple. And you also can simplify this expression here by taking into account that the relative velocity between the projectile and the target, the initial relative velocity, it's h bar k divided by mu. And when you do that, what happens is that you have and this is what you get. So you solve the equation. You go from a very complex equation to something much simpler, and it's actually equivalent to a time-dependent Schrödinger equation. If you replace z over v, if you replace it by t, you get a time-dependent Schrödinger equation. And so what is good is, as we've just seen, we know exactly how to solve the time-dependent Schrödinger equation. So we have codes to solve that accurately, and so we can use these codes. The only thing is, it's mathematically equivalent to time-dependent approximation, a time-dependent Schrödinger equation, but there is no semi-classical approximation here. It's a fully quantal approximation. And so we have done that. It was the PhD thesis of Gerald Goldstein, and we published that in 2005. But another group, the group of Ogata-san and collaborators, did a similar work using CDCC, and they call that eCDCC for iconal CDCC. It's the same kind of idea, but it implemented in a couple channel code. And so the cross section, when you do some calculation, the cross section can be obtained from this development with this S wave, S matrix, if you want, obtained from the projection of the solution for Z going to infinity onto the eigenstates of the in the continuum. The big difference with the semi-classical approximation is that here you sum amplitudes. So you include the interference, the quantal interferences are taken into account, you sum the amplitude, and then you take the square modulus. Whereas in the semi-classical approximation, if I go back somewhere here, you first take the square modulus, and then you do the integration over the impact parameter. That's a big difference. So here we should see the dynamical. We should see the quantal interferences between the different trajectories. Now, this is what we call the dynamical Iconar approximation. This is different from what people usually understand as the Iconar approximation. In the usual Iconar approximation, so something that Jeff Tostervin has developed with Gregor Hansen, has an additional adiabatic approximation. They say we are at high energy, so we can neglect the excitation energy compared to the beam energy. And so what they do is, this is the equation, and they neglect that part of the term. So they neglect the dynamical effects. So the coupling, the dynamical effects in the reaction. And the good thing is that then you can solve that exactly analytically, and you just have what is called the Iconal phase, which is the integration of the potential over on straight line trajectory. So that makes the whole thing simpler. Now, does it work? So it looks nice, but does it work? So here are the data of Fukuda et al. For the breakup of beryllium-11 on lead. Breakup cross-section as function of the scattering angle in this case. So beryllium-11 enters, breaks up into beryllium-10 and the neutron, and they are scattered in their center of mass is scattered in the direction theta. And so the data are the points. and the calculation of, in this case, that was Gerald who did this calculation, is the red solid line here, and we see that they agree very well with the experiment. When you perform the usual Iconar approximation, it works fine here. That's the orange dashed line, but at forward angle it diverges. Do you have an idea why you have that? Okay, it starts to be late in the afternoon. So the problem here is that that's the region where you are Coulomb dominated. And so make the adiabatic approximation so that the projectile can be seen as frozen is not fine because you are dominated by the Coulomb interaction. And you can never say that the collision time in a Coulomb dominated reaction is small. So you cannot consider that the projectile can be seen as frozen because it's in the Coulomb interaction that is long ranged, and therefore there is no way this can work, and it diverges. So Jérôme developed a nice correction to that, a semi-classical correction with Angela and David Brink, which corrected that, still keeping the same simple way as the Iconar approximation. So that's a very nice model to, a very nice way to solve this divergence here. So how do these different models compare to each other? We started for a different reason, but then eventually Henning Benson, Philomena Nunes, and myself, we perform a calculation within the three models. So CDCC, that's the green solid line, the time-dependent approach by Henning in blue dotted line, and our dynamical Iconar approximation in red dashed line. This is the breakup cross-section as function of the energy for the carbon-15. So that's the same data that I've shown before by the same calculation by Henning. And we see that the three calculations are basically on top of each other. So it was a pain because you need to make sure that you are comparing the same thing, that you're using the same optical potential, that you use the same description of the projectile. It takes a while to make sure that all the constants are exactly the same, but once you've done that, they basically give you the same answer. They're also very good agreement with the data. This was a detail. That was not the goal of the paper. The goal of the study was to confront the models with each other, but we are in good agreement with the data, and we are very happy with that. We looked then at other observables, and that's where the problems start to arise. So we looked at the angular distribution. So once again, it's the breakup cross-section, but looked at as a function not of the carbon-14 core neutron relative energy, but as a function of the scattering angle of the center of mass. And as expected, this should have oscillation exactly as what you've seen this morning with the calculation. You know, you have this sort of Coulomb rainbow there, and then you have oscillation at forward angle. That's exactly what we obtain here. The CDCC calculation, so the fully quantal one, has oscillation, time-dependent calculation, no quantal interferences, no oscillation. So there, that's the problem. But the good thing is that it follows, basically, it goes through these calculations. So you miss that, but you assume that it's still not a bad approximation because you go through these oscillations. The dynamical calculation, dynamical Iconar approximation has the same oscillation. They are basically nearly at the same place, so they agree very well. So that's a very good thing, because you gain a factor of, I think in these calculations, you gain about a factor of 100 in the computational time. So that's something that is worth doing. And so we did that, and we thought, okay, this is 70 MeV per nucleon. What happens if we move down lower energy? That's where the Iconar approximation fails. So we moved down to, we first tried 40, no significant difference. We went down to 20. 20 there you start to have a problem. The icon approximation has a cross section as a function of the energy, which is too high, and the oscillation, you still have the oscillation, but they are at too forward an angle. So everything seems to be shifted. The time dependent, on the other hand, works very well even at low energy. So it agrees with CDCC, and as we've seen before, it agrees with CDCC on average without the quantal interferences. So without the oscillation, it agrees with the CDCC calculation. So we repeated we said why. What's the problem? And the problem is due to the fact that you use a classical trajectory, a Coulomb trajectory, and so you move away from you include the Coulomb deflection, and that's why you go to larger angles. If you look at the straight line trajectory, then you get the black dashed dotted line here. You have the same kind of behavior. You are also too high, and this is due to the icon approximation where you have this plane wave approximation. You neglect the Coulomb deflection. That's what I've mentioned before. So there, even at 20 MeV per nucleon, you need to include this Coulomb deflection. And so we tried to understand what the problem was. So we worked with Fukui and Ogata from Osaka at the time. Now Ogata is back to Kyushu. And so we looked at their iconal CDCC. We thought, okay, it's a problem of energy conservation at one point, but that's not the case. Iconal CDCC does not do a much better work. But we looked as a function of the impact parameter. We saw that there was a sort of a deflection here. We did not include properly the deflection due to the Coulomb interaction, and so what they suggested is to use a Coulomb correction where you replace the impact parameter by the distance of closest approach in a Coulomb trajectory, and there we get with the iconal approximation, we get the right behavior. So that was the problem. The problem is the Coulomb approximation, and so we could solve that by a sort of a trick by solving this changing the impact parameter. And so I come to an end here. So the breakup is described here in a few body model of the reaction. Projectile is seen as a cluster. The target is supposed to be one big chunk, and the interaction is described by optical potentials and phenomenological interaction. We've seen three different models, so CDCC, the time-dependent approach, and the iconal approximation. Each one of them have their advantage and disadvantage. CDCC, fully quantal, conservation of energy, fine, but it requires the continuum discretization, and it's very heavy computational. You solve the computational problem is solved by the time-dependent approach, but you miss the quantal interferences. And the iconal approximation restores the problem of the quantal interferences, but it's only valid at high enough energy. So you have to. There is no free lunch. Okay, so you gain something, but you lose something when you do these approximations. So the important message here is know the range of validity of your model before you try to extract anything from the data. And so we'll see tomorrow, we'll see more about what we can actually infer from the data. And I think I will stop here.